Let me start with some motivation. The last decade has really been transformed in a lot of ways by deep learning. It currently affects how we work, how we play, almost every aspect of life, medicine, education, product design, entertainment, has really been transformed by deep learning. And what's interesting is that this was enabled by hardware, by GPUs in particular. If you look at what makes deep learning work, there's really three key ingredients. The first, which I've sort of illustrated by the schematic of AlexNet at the bottom here, is algorithms. And most of the algorithms used for deep learning were developed in the 1980s or earlier. So deep neural networks, convolutional neural networks, training them with backpropagation and stochastic gradient descent. I can point you to the papers in the 1980s for all of those, and in some cases earlier than the 80s. So that technology was around. The next thing that was required were data sets large enough to train these neural networks to get a level of performance better than the alternative techniques. And data sets like Pascal and ImageNet came around in the early 2000s. But it wasn't until we had hardware that was fast enough to train a large enough neural network on a large enough data set in a reasonable amount of time, where reasonable for most people seemed to be about 2 weeks, that the blaze was actually ignited. So you can think of the GPUs as being the spark that ignited this fuel-air mixture of data and algorithms. And since then, it's really been amazing. They've it basically replaced all previous computer vision algorithms in cases like image classification, which is what ImageNet was about, detection on images, and in speech, doing both automatic speech recognition on the waveforms and then doing various natural language tests. They become the way everybody does business, doing time series analysis, and playing games like Go and chess. They've kind of have taken over everything. And as they've done that, the demand on hardware, for both training and inference, but this graph shows training, has grown by orders of magnitude. Between AlexNet in 2012 and ResNet in 2016, there were about 2 orders of magnitude increase in the training petaflop per second days needed to train an image network. And this doesn't really account for the fact that in the middle here were a bunch of techniques developed that basically made these networks much more efficient. And if those hadn't been developed, it would have been yet another order of magnitude. More recently, this line on the right shows the trend line for language models, starting with BERT in 2018, and just a couple of years later, GPT-3. And here there's close to 4 orders of magnitude of increase in the computational demands of training over just a couple of year period. And this is really getting us to the point where what we can do with deep learning is gated by hardware. People would like to do even larger language models, train them on even larger, unsupervised data sets of language, but they're very much limited by what they can do even with 4,000 GPU clusters in a reasonable amount of time. And so the pressure is really on to continue scaling deep learning performance. And this is true, across lots of different domains where we're tagging lots of images, we're doing lots of searches. Recommender systems are a big application for deep learning, deciding what things to stick up in front of customers on the web, scanning medical images, looking for fraud. In both the complexity of the models and their pervasiveness and how often we're using them, things are ramping amazingly. So let me go through a little bit of history about how we've gotten to where we are, and then I'll talk a little bit about the future. So this chart shows inference performance over 8 years from when we introduced Kepler in 2012 to Ampere just last year. And the performance over these 8 years is 317x increase, something we've come to call Huang's law. And this is way faster than Moore's law performance increase. And it's also, unlike Moore's law, not at all due to process technology. These chips are in 3 different processes. I've color-coded them. The early ones were 28 nanometer chips, the Kepler and Maxwell. The Pascal, Volta, and Turing, the Quadro 8000s, the Turing-based GPU, were in 16 nanometers. Some of them were labeled 12, but they have 16 nanometer metal rules, so I call them 16 nanometers. And then Ampere is a 7 nanometer part. And the performance improvement due to process technology is maybe 1.5x, perhaps 2x at the outside. Almost all this 317x is due to architecture and cleverness in circuit design. So let me talk about how we got there. So in Kepler, this was a GPU that we designed without thinking about deep learning at all. We started some of our activities in NVIDIA research in deep learning around 2010. And it really had not moved at all into the planning stages of GPUs to plan features to make them more efficient with deep learning. So this was a part that was designed mostly for graphics and a little bit for high performance computing. And therefore, what it really had to offer was a lot of floating point 32 performance. And so here we have 4 teraflops of FP32 and 250 gigabytes per second. So we'll sort of view this as the baseline. That's 1 on our performance graph. The next thing we did was Pascal. We did a couple of things here to make its deep learning performance better. The first is we'd realized by 2016, by a bunch of studies we had done, that many neural networks, not all, but many, could be trained with FP16. And so we basically put in really good support for FP16 in Pascal. So, we had 10 teraflops of FP32, which is pretty good compared to the roughly 4 in Kepler, and then twice that much, 21 teraflops of FP16 performance. We also added complex instructions like a dot product for instruction. And what this did is it let us amortize the overhead of instruction fetch and decode and operand fetch over 8 arithmetic operations rather than the 2 we had previously with the fuse multiply add instructions. So that basically let much more of the energy in the part go to actually doing the math and less to doing the overhead. In Pascal, we also introduced HBM memories as 732 gigabytes per second, 3 times the bandwidth of Kepler, because many of these deep learning benchmarks are bandwidth bound. And we added NVLink, so we could start to scale out these machines to do larger training in clusters of GPUs. And we introduced the first DGX boxes of 8 GPUs in the Pascal generation. So moving on up the chart, the next step, which is a big step up, was with Volta in 2017. And what we did here is we finally realized, okay, we need to do something more to amortize out the instruction overhead if we're going to have a really efficient deep learning machine. So what we essentially did is we built a deep learning accelerator, which we called the Tensor Core, and we attached it to the GPU by making it accessible as an instruction. The key instruction here is HMMA, half precision matrix multiply accumulate. And what it does is it takes 2 half precision, 2 FP16 4x4 matrices, multiplies them together, and then sums them into an FP32 matrix. And that is the inner loop of almost all of the deep learning algorithms. And so by basically making that an instruction, we're able to amortize out essentially all the overhead of instruction fetch and decode. There's, like on the order of 10 to 20% overhead. The rest of it is payload math. That sort of bounds what somebody building an accelerator can do better than this. We basically have made it so, such a large fraction of the energy and area going into the math of deep learning that you can't do a whole lot better by throwing away the programmability, and you lose a lot by throwing away the programmability. We also went to a better version of HBM, bumped the memory bandwidth up to 900 gigabytes per second. And we added a new version of NVLink that doubled the bandwidth for building clusters. And in this generation, we introduced NV switch so that you could tie together multiple GPUs. In fact, the NV switch, although we never built a machine this large, was scalable up to 1,024 GPUs that could be built as a big shared memory machine. So that moves us up to this data point here. With Turing, we basically realized that tensor cores was such a success that we added integer tensor cores because most of, while FP16 is suitable for training almost all networks, you don't need that much precision or dynamic range for inference. You can do inference quite well with integer 8. And so in Turing, we introduced integer tensor cores and essentially doubled the performance. So we get, a quarter of a petaflop of int8 performance with the integer matrix multiply accumulate instruction. This particular part actually used GDDR memory because we wanted to get enough bandwidth to be able to support a lot of the natural language models and recommender systems that were very bandwidth intensive. And some people compared this unfavorably on an energy basis against some accelerators that were available at the time. But if you actually did the numbers, you realize that our math was actually more efficient than the accelerator. And the entire difference in energy was attributable to RG5 memory compared to their LPDDR memory. And that was a trade I think we made in the right direction, because we were able to support models that they were unable to support because they had inadequate bandwidth. It's sort of tangential to the deep learning discussion, but another thing I'm very proud of with Turing is it introduced hardware support for ray tracing with our RT cores, a project that we started in NVIDIA Research in 2013, and made it to product just 5 years later. So that gets us up to the Quadro bump here, and then we have the big jump up to Ampere with 1,200 teraops of performance. And the big win in Ampere, there are actually a bunch of really neat innovations in Ampere, but the big one was support for sparsity. So it turns out that most neural networks are fundamentally sparse, in the sense that you can prune them, you can remove a large number of the weights with no loss of accuracy. But the level of sparsity puts them in this really awkward place where convolutional networks tend to be 30 to 40% dense with no loss of accuracy, and fully connected networks somewhere between 10 and 20% dense with no loss of accuracy. And conventional wisdom in the numerical analysis community is that until you get down to 1/10% dense, the overhead of running the sparse matrix package makes it better to run the dense matrix package. Starting with some research at Stanford, we've been working on sparsity for some time. We've been able to build machines that are very efficient at even say 50% density. But being able to get it better than dense with power gating, which was what we were competing with the previous designs, was actually hard. And the thing that really got us over the hurdle with Ampere was realizing that we wanted to do structured sparsity. So Ampere supports a version of sparsity where you insist that no more than 2 out of every 4 entries are non-zero. You then basically compress these weights by discarding the non-zeros and put in a little code word which says which of the 2 weights are the ones that you have. And then we basically use that code word to figure out which of the input activations to multiply by the non-zero weights, sum them normally to do the dot product. And this works extremely efficiently and essentially doubles our performance on most neural networks. Ampere introduced a bunch of other neat innovations. It introduced what we call TF32 for TensorFloat 32, which is basically the exponent of FP32 with the mantissa of FP16. So it gives you sort of the best of both, BrainFloat and FP16. We also supported BrainFloat, which is just truncated FP32. You have the exponent of FP32 and truncate the mantissa. And we support this structured sparsity in all of these data types. So you get it for training with FP16 or TF32, and you get it for inference with int8 or even int4. And as we've gotten better at doing our quantization, there are actually a lot of networks that we can implement in int4 with no loss of performance. We added 6 stacks of HBM and used a better version of HBM. You get up to 2 terabytes per second of bandwidth. And so a good figure of merit for me is teraops per watt. And I'll come back to that when I talk about accelerators later. And for int8 inference, we're at a little over 3 teraops per watt, and for int4, we're over 6. So to sort of summarize, this is sort of, deep learning past, what really accounted for this 317x in 8 years is, 3 things. The biggest one was number representation. FP32 is overkill. Those are expensive arithmetic ops to implement all your deep learning, particularly your inference with. Going down to, int8 in Turing and Ampere really gave a big boost in performance per watt. In fact, when the first paper on the TPU-1 came out, they claimed that all of our advantages in energy are due to being specialized. In fact, they were comparing against Kepler, and all of their advantages in energy could be attributed to comparing int8 against FP32. The next way we gained performance was by adding complex instructions, starting with the dot product instruction in Pascal, and then by adding the matrix multiply accumulate instructions in Volta, Turing, and Ampere. And what these do is they amortize out the overhead. So there's no disadvantage to having a programmable engine. It's as efficient as an accelerator because each instruction does so much work, the overhead of the instruction is negligible. And then finally, a very small amount came from process technology, moving from 28 down to 7 nanometers. To drive home the point about amortizing overhead, One way to think about it is if you're doing a half precision floating multiply accumulate, your overhead is about 2000x. You're spending 20 times as much energy on the 30 picojoules to fetch, decode the instruction, fetch operands and the like, than you are on the 1.5 picojoules to do the multiply and the add. When we moved to dot product, we got the overhead down to merely a factor of 5, because now we're amortizing 8 operations rather than 2 over that 30 picojoule of fetch. And when we move to HMMA, we now have the almost all the energy going to payload. The overhead is only 22%, and with IMMA we got it down to 16%. So at this point, the differences in quality of design is far more important than the little bit of overhead that you get by making it programmable. So I talked mostly up to now about the performance of a single GPU, but with these large language models, a single GPU is not adequate to train them. So in parallel with these developments, starting with the introduction of NVLink and Pascal, and then NVLink 2 with Volt and NVLink 3 with Ampere, we basically doubled the bandwidth on each of those generations. We introduced a first generation NV switch in the Volta generation, a second generation switch with Ampere. We've enabled people to build very large clusters of GPUs, and we sell the DGX boxes, which are each of these little gold-faced chassis here. And then with our Mellanox acquisition, we now can sell the complete solution of the data center quality switches and interconnect to build very large GPU clusters. And we've made this with the DGX SuperPod product something where you can basically buy a pre-configured machine that you can deploy it, and it will be in the top 20 of the top 500 list. Whereas typically in the past, each of those were kind of a bespoke, custom-built machine. And these machines, while they're also great for scientific computing, for the most part, people buy them and they use them for deep learning training, because it takes, in many cases, months of time on one of these machines to train a single very large language model. But enabling this scale out is just as important as improving the efficiency of the single GPU to enable the entire solution. So let me shift gears here a little bit and talk about accelerators. And in NVIDIA, we actually view our accelerators as a place we can experiment with new techniques that we figure will ultimately be incorporated into the mainstream GPUs. And one way to think about these accelerators is they all have a matrix multiply unit fed by a memory hierarchy. But then what's really important is how you organize that so that most of your energy goes into doing those matrix multiplies and not into moving data around. Our first effort at this, we kicked this project off, I think about 2013, was the NVIDIA DLA. It's an open source product. You can go to nvdla.org. You can download the RTL for this and all the tools for this. And it's very, very well supported. And so it's very, very much like other deep learning accelerators, and that is a big MAC array. In this case, it's 2K innate multiply accumulates, or 1024 in 16, or 1024 FP16. The two things it had, I think, that were quite unique when we first launched it were its support for sparsity. And so we basically picked the low-hanging fruit on sparsity here, which is all of the data movement from DMA into this unified buffer, and from the buffer, out of the buffer until we launched into the MAC array, were done with only the non-zeros stored, and then a encoding to say which elements those were. And we expanded those elements as we fed them into the MAC array. Now, we expanded them in kind of a clever way. We actually didn't feed a 0 into the MAC array when we had a 0, because that would toggle all the data lines to 0. And then on the next non-zero, all of them back up again. So instead, what we did is we sent a single wire that said, I am a 0. And when you got that wire at a multiplier, on either input, you basically lock the data on that multiplier so nothing would toggle. And the multiplier would send an output saying I am a 0, which would basically cause nothing to be added in on the output. And that data gating was extremely efficient in basically getting most of the energy gain you can get from sparsity. We didn't get the advantage of using the multipliers on other non-zeros, but we got almost all of the energy advantage. The other real innovation in the NVDLA was we put in hardware support for doing Winograd transforms. As everybody who's taken a signal processing course knows, that if you want to do a convolution, let's say an n by n convolution kernel, that takes n squared multiplies and adds to do in the spatial domain. But if you do it in the frequency domain, it's a pointwise multiply. And so it's much more efficient with large convolutional kernels to do them in the frequency domain rather than the spatial domain. And rather than using a Fourier transform here, we're using a Winograd transform, which is a pretty efficient way to do this. And depending on the size of your kernels, this will wind up giving you a factor of 4 improvement in performance for certain image networks. At Stanford, we're working with my student at the time, Song Han, who's now a professor at MIT. We developed the efficient inference engine. This was at ISCA in 2016. And its real contributions were, this is one of our first efforts at sparsity. And so we basically had hardware support for a compressed sparse row representation of the matrix. And it was extremely efficient. It basically was as efficient. It was efficient enough that at 50% density, you had a savings over doing a complete dense calculation. But that's because the arithmetic units were scalar. It was doing a single multiply at a time. What we found later is that to build efficient accelerators, you want to build arrays of vector units. So you don't, so each engine isn't doing a single multiply add. It's doing 16 wide multiply adds for 256 multiply adds per cycle per PE. And it was when we started going to those arrays of vector units that we had trouble making sparsity work efficiently and needed to move to structured sparsity. For the EIE, taking a scalar unit, it worked really well to simply store the pointer structures in a separate memory and have a pipeline stage that walked the pointer structures, decided which data had to multiply with which other data, did the multiplies, and then stuck the results in the correct locations. That actually worked extremely well and was very efficient for scalar units. The other thing we did in the EIE is we realized here that in addition to pruning, the other thing you could really do to get neural networks efficient was to quantize them well. And so here we basically decided to use codebook quantization. And in terms of the number of bits used to represent something, you can't do better than codebook quantization. So we basically trained the codebook. It turns out if you use back propagation, stochastic gradient descent, you can back propagate in anything. So we back propagated into our codebook, and we trained the optimum set of code words given a precision. Given you had 7 bits, you're going to get 128 code words. We would train the optimum 128 code words for that neural network. The problem with codebook quantization is the overhead of the math gets pretty high, both because you need to do the codebook lookup, which is essentially looking up in a RAM, whatever the size of your codebook is, what the actual data value is. And then the actual data value has to be represented in high precision, but you can't represent those code words accurately. So we wound up paying for the energy of high precision math, which wound up making it, it was great from a compression point of view, not so great from a math energy point of view. And so we kind of dropped that technique in later units. Joel Emmer at NVIDIA, working with Vivian C at MIT, built Iris, and its contributions really were figuring out tiling, or basically how to block the calculation so that you get minimum data movement. And the typical one is what's called row stationary, where you propagate the weights across the rows and then the output activations down the columns and minimize the energy due to data movement. Still working on sparsity, we built a machine in 2017 called SCNN for sparse convolutional neural networks. And what we did here is we moved all the complexity of dealing with the sparsity to the output. So we basically would read all the input activations and where they need to go. So think of this F-wide vector here as a vector of input activations. Typically we would do sort of 8 at a time, and then we would read it'd be like 4 at a time, then we'd read 4 weights at a time. Then every weight would need to multiply by every input activation. It's just a question of where you put the result. So we do F by F multiplies. The coordinate computation would take the index of the input activation, the index of the weight, and figure out where in the output activation that result needed to be summed. And then we did a scatter add computation on these accumulator buffers. And everything was really efficient right up till that point. But it turns out that it's not a good idea to move your irregularity to the output, because that's where you actually have some of the widest precision. You tend to accumulate, you're doing 8-bit weights, 8-bit activations, you'll accumulate to 24 bits. So you're doing a lot of data motion here with wide accumulators. And even though we were extremely efficient right up to all this stuff in red, this wound up sort of making it was a little more efficient than doing a dense one, but not as much as we thought. We're down to maybe 50% the energy of a dense unit, but only a few percent better than the orange bar here, which is really the MDDLA. That's a dense unit with data gate. Another neat thing we did, though, is we took some of these accelerators we built, and we built a multi-chip module with them. This is, Simba, the chip. We tend to give our chips great names like Research Chip 18 for the research chip we did in 2018. And this demonstrated a lot of neat technology. It was a nice architecture for the PEs, an on-chip network, an off-chip network, very efficient signaling technology between these, and scaling up to the full 36 chips, each of which had a 4x4 matrix of PEs, each of which, I think in this unit was eight wide vector units per PE. We get 128 teraops, and we're at 0.1 picojoules per op, which is around 10 teraops per watt for this unit. And we learned a lot about the trade-offs here, and we realized that building these arrays of PEs, there's a very large design space of how you structure your memory hierarchy, how you schedule the data. And so we built a system we call Magnet, which is a design space exploration system. This is published at ICCAD in 2019. What it basically does is it enumerates this design space of, how wide should each vector unit be, how many vector units per PE, how big are the weight buffers, how big are the accumulator buffers and buffers for the activations. Then we actually realized that we needed to do sort of another level of caching. And we added weight collectors and accumulator collectors to this. And with this extra level of caching, we're finally able to get to the point where this shows these are the different data flows here, that with the weight stationary data flow that was originally done by Z and Joel, you have most of your energy going into things other than data path. It's in the accumulation buffer, the weight buffer, and the input buffer. But with these hybrid data flows, the weight stationary, local output stationary, local weight stationary, we're able to get almost 2/3 of the energy in the math and make much less of it be in these memory arrays by basically staging things at yet another level of memory hierarchy. And with that, I don't have the number up here, we were able to get up to about 20 teraops per watt of performance. More recently, and this is quite recent, this was at the ML-SIS conference this year, we introduced something called VS Quant. And this is really getting to how to do quantization in a way that's not just efficient from a bit, the number of bits used from the compression point of view, which that codebook quantization was really good for, but how to make the math really inexpensive as well. And so what we do is we use an integer representation, but we want to scale that integer representation so that the dynamic range of the integer that you can represent, say it's like -127 to 127, is compressed to lay exactly on the data in the most relevant way. Now it turns out that if you do that over an entire neural network, it doesn't work well because there's so many different dynamic ranges going on there. So the key with VS Quant is we actually have a separate scale factor for a relatively small vector on the order of 32 weights. And by doing that over those 32 weights, there's a much smaller dynamic range. We can drop those integers right on top of them and clip them optimally as well. So maybe the outliers don't get represented as accurately, but we sacrifice that for better representation of the rest of the numbers. And doing this, we're able to get quite good accuracy with relatively low precision weights and activations by making every bit of those weights and activations work a whole lot better. So we now have multiple scale factors, one for the weight, one for the activation, and we basically do that at the vector level. The results are sort of shown here. With BERT base, we're able to train things and get energy savings of 20% and area savings of in some cases up to 70% compared to doing it without this weight training. And the color coding here is green has essentially no loss of accuracy, and the blue, orange, and red have exceedingly larger loss of accuracy. But even at the blue level, which is pretty good accuracy, we're able to get pretty big savings compared to without doing VS Quant. With VS Quant and a few other tweaks, we basically have demonstrated on these language models, which by the way are much harder than the image models, on the order of 120 teraops per watt. With accelerators, what we do is we start with a matrix multiplier. We need to come up with a tiling, a way of taking the sort of 7 nested loop calculation of a neural network and essentially, duplicate some of those loops into levels of the memory system to maximize reuse from each level of the memory hierarchy and minimize the amount of data motion. So we are making very few references where they're expensive, certainly hardly any from off-chip DRAM, but even from the on-chip global buffer, it's pretty expensive. And getting most of them out of those very local collectors, or even better, just letting the input of a multiplier sit there for 8 cycles while you do 8 multiplies by the same number. We also have explored sparsity. It's great on the compression side. It basically increases your memory bandwidth and your communication bandwidth, reduces the energy of both memory and communication. The next level of sparsity is to data gate. When you have a 0, just send along a single line that says I am a 0. You don't have to toggle 8 or 16 bits each cycle. And then with Ampere, being able to reuse the multipliers by using structured sparsity, which is an efficient way of doing that with the overhead of a couple of multiplexers and essentially negligible pointer manipulation and the like. We're able to reuse the multipliers and get a 2x in performance. And then number representation is really critical. We started out with the EIE trying to do code books, but that makes the math expensive. Scaling, like with VS Quant, puts the bits where they do the most good, and you want to scale by relatively small vectors. And the way we like to think of this is what works in an accelerator will ultimately become part of the GPU. It's a great way of test driving things because the GPU, as we see it, is a platform for domain-specific hardware. It's got a really nice memory system, a really nice network, and places to bolt on things that make certain applications go blazingly fast. So that's sort of think of it as deep learning present. Let's go talk about deep learning future. So here's my pie chart of where the energy goes. And this is, for a particular version of a magnet generated accelerator. You see a lot of it is in the data path in MAC. It's about 50% is math. So we want to make the math cheaper. And a lot of the rest of it is in memories and data movement, right? We've got the data movement is green. In each of these, other segments, input buffer, weight buffer, accumulation buffer, and accumulation collector are different memories. So what we're looking at is make the math cheaper. One of the best ways to do that is to move to the logarithmic number system, because in a logarithmic number system, the multiplies turn into adds, and adds are generally a lot cheaper to do. The other thing to do is to move to smaller numbers, and this is a little bit of what we did with VS Quant, is by quantizing more precisely, we can get the same precision out of a neural network with lower precision numbers. We want to do better tiling by perhaps in some cases adding more levels to the memory hierarchy so we can lower the memory energy. There's also opportunities for circuits here to make memory circuits more efficient and communication circuits more efficient. On Ampere, we've sort of had a first cut at structured sparsity, but I think we can do better by pruning the activations as well as the weights by going to lower densities or perhaps a selection of multiple densities. And then, process technology will still get us some capacitance scaling as we move down. So when we talk about the logarithmic number system, so this is the value function here. The value of the number is, -1 to the sign bit times 2 raised to what's essentially a binary floating point, binary decimal number, EI.EF. So EI is the integer part, EF is the fraction part. The way to think about this is we're really raising, a root of 2 to a power. So if, for example, we have 3 bits of EF, we start with the 8th root of 2, and then are raising. You can think of it as a number over 8 is the exponent. And you need that fractional part, because if you just represent your logs with an integer part, you can represent 1, 2, 4, 8, 16. The gaps between numbers are too big. You need the fractional part to make the precision good enough. You get lots of dynamic range if you have a big EI, but you need the EF for precision. And the way to think about this is this particular representation, you can it's 4.3, has a dynamic range of 10 to the 5th, which is kind of what you get out of FP16, and a worst case accuracy of 4%. In contrast, int8 has a dynamic range of 10 to the 2, So 3 orders of magnitude worse dynamic range. And its worst case accuracy, which happens at the very low end, is 33%. And you can apply offsets to this to make things work well. Of course, numbers near zero, you have to be kind of careful with. So any of you who are of my generation will remember that in school, we basically did most of our engineering calculations with things that looked like this. I still have 1 or 2 of these lying around for old time's sake. But this is how we did our math. This is the log number system. Slide rules encode numbers logarithmically in position. So you can do a multiply by essentially adding the distance, and then you look up the result of that multiply. This plot of 4-bit log representations illustrates why they have so much better accuracy than integer representations. And it's because they have, for the 4-bit representation, a constant error as a fraction of the number. So if you view your error as delta over magnitude, it's the same everywhere on this chart. It's 9%. You have small errors with small numbers, big errors with big numbers. When you use an integer representation, the error is the same magnitude everywhere. So you have a big error with a small number and a small error with a big number. And the problem is, if you look at the distribution of weights in a neural network, they're clustered around 0. So you have the big errors right where most of your distribution is, right? So the bulk of this distribution here is where the errors of that integer number system are largest. And you have only a few weights out in these wings where you wind up getting small error with the integer representation. So the log representation does much better on this. So it turns out that using a logarithmic representation makes the multiply really cheap. Historically, then you get bit by trying to do the add, but it turns out there's a very clever way of doing the add that isn't very expensive, and I will let you read this patent application if you're interested in that. So let me talk a little bit about sparsity. Getting a real energy win from sparsity compared to data gating, which is amazingly effective, is actually surprisingly difficult. I don't want to tell you how much time I spent, chipping away on that one with limited results until we hit the structured sparsity. It's really easy to reduce your number of arithmetic ops, but then wind up seeing big energy increases swamped by irregularity, particularly due to glitching. So it turns out that a lot of these schemes for sparsity involve kind of scanning, your index vectors that say where the non-zeros are, and using that scan to compute the select input of a multiplexer, and then selecting the ones you want to multiply by those non-zeros. And if you're not really careful, you wind up toggling that select input of the multiplexer many times in a clock cycle. And so its output toggles many times, and that burns gobs of energy due to glitching. When we first did the comparison and we didn't have our power flow done right, so we weren't accounting for glitching, we thought we had success, but then we finally actually did a real simulation accounting for glitching. The results were awful. We'll often get increases of 4 or 5x due to the glitching effect. So the Ampere structured sparsity is a great start. I think we can do a lot more by applying sparsity to activations and by applying lower density, so you can select on a per layer basis or even a per vector basis, whether you want to dial in the 50% sparsity, which is what we have today, or 25% or 12.5% or something like that. So almost half of this pie chart is memory. It turns out that these are small read mostly memory arrays. And there are a couple of things you can do. One that we're already doing is making them latch arrays. But the other thing you can do is our latch arrays tend to burn memory on read by having a sort of a read bus that you then essentially have a transfer gate that you take the selected cell and dump it on the bus. An alternative approach is to bring, because they're small memories, like 4 entry or 8 entry memories, you bring all 8 entries out right to the input of the multiplier, and you put a multiplexer there. And that way, when you switch the read address, no long lines toggle. You toggle those lines when you wrote the memory, which you did rarely. And then when you read them, which you do often, all you have to do is pay the energy of the multiplexer. And then the other thing to observe is that most memory energy is actually communication energy. The actual energy required to write or read a bit cell is almost negligible. The energy is basically taking the data from wherever it is to the bit cell, or taking it from the bit cell to where you want to need it. And we can do better on communication. And the communication also helps with the networks on these chips. This is one concept that we published at ISSCC back in 2016, where we essentially get a 4x energy savings by taking our power supply and splitting it and signaling both on the high end of the power supply and the low end of the power supply. So it's basically cutting the swing in half, which gets a 4x energy savings because of the V squared factor. So all the numbers I've been giving you so far normalized to 16 nanometers because I wanted to factor that out and compare the different techniques. And even though sort of Dennard scaling is dead, we're not able to scale the voltage under the constant field scaling laws as we move to new process technologies. The capacitance still does scale. It's less than linear because the complex rules that come with multi-patterning and FinFETs and all of that. But you could expect going down to 5 nanometers, another factor of 2 to 2.5 in energy. One thing we played with, which doesn't work, and we wrote the paper in DAC, which explains why it doesn't work, is trying to go to analog. A lot of people have tried to use, essentially resistors of some type to do a matrix vector multiply in the analog domain. You basically, your matrix is in the resistors. You apply a vector on one, say the row lines. You sum the currents on the column lines, and you've done, a matrix vector product in the analog domain. The problem is, even if that was free, the cost of doing an analog to digital conversion is high enough that if you want to match the precision of int 8, you'll spend, over a picojoule per Mac doing that calculation. And that's sort of less than 1 teraopt per watt. Well, we're doing int 8 calculations these days at 120 teraops per watt. This is actually slightly pessimistic. We've since redone these numbers by applying some of the quantization techniques, where this assumes you're going to do your analog to digital converter for the full dynamic range you need. But if you do some clipping and you throw away both some low bits and some high bits, you can do a little better than this. You can essentially move 2 lines down on this plot. You're still going to be getting sort of 3 teraops per watt. That's what Ampere gets today, and not the 120 teraops per watt you can get from a digital accelerator. So let me wrap up, and then we'll leave a few minutes for questions. So our GPU inference performance has been doubling every year since people started using GPUs for deep learning with Kepler in 2012. Think of this as the deep learning path. This history getting to where we are today is largely better number representation, moving from the FP32 of Kepler to FP16 to int 8 to int 4. And by amortizing out the instruction overhead, by having more complex instructions, going to dot product in Pascal, the half precision matrix multiply accumulate in Volta, and the integer matrix multiply accumulate in Turing, doing structured sparsity in Ampere. And I didn't talk much about it, but plumbing is really important here. By plumbing, I mean arranging the on-chip memory system and network so that you can feed these voracious tensor cores. You've got a tensor core doing peta operations per second in Turing, and keeping the data fed into that, doing common benchmarks is a non-trivial exercise in arranging the off-chip memories, the on-chip memories, and the interconnect between them, and making that all work really well. So looking to the future, we tend to play with accelerators as a way of experimenting with new techniques. And I described to you over the years a number of experiments we've done with sparsity, with different tilings, and eventually writing this magnet program to experiment with different tilings and configurations and the like all simultaneously, and with number representation. And so there's pressure on us, since, as I said, progress in deep learning is gated by continued performance in hardware. And we feel a lot of pressure to keep doubling every year. And by the way, after you play these cards, they're played. You got to come up with another card to play next time. So how do we do that? I'm very optimistic about new number representations with log numbers and even more clever quantization schemes beyond VS Quant. I think we can do better on sparsity. I think there's some circuit cards to be played for the memory and communication parts of that pie chart. And we still have some process technology to move with. So with that, I will, here I am on the lovely shore of Lake Tahoe, and I'll open it up to questions.
Excellent. Thank you very much, Bill. I'm going to read you the questions. I'm going to skip if there are repetitions. How large of a matrix convolution do you need to make a Winograd transform the more efficient way to do the operation?
Well, I think you get some efficiency even with a 3x3 convolution. I think it's like a 2.5 times gain. But as you get bigger, the efficiency gets better.
Okay, how NVIDIA processors and accelerators are used to support the Netaverse?
So that's a really good question. So there's a lot of different parts of our version of the metaverse, which we call Omniverse. And part of it is graphics. We have a really great computer graphics engine built into Omniverse so that as you create a virtual world, you can render it. And for people who are there, whether it's via virtual reality goggles or via screen, it looks like the real world. And deep learning is completely transforming. It's like it's transforming everything else. It's completely transforming computer graphics. And I see this transformation happening in two ways. The first is taking the conventional graphics pipeline and kind of deep learningizing it. And so this affects very many places there. The biggest ones are in things like anti-aliasing, scaling, and denoising. So one of the techniques we apply in modern GPUs, and it's certainly part of Omniverse, is we will render an image at a lower resolution, and then we'll apply a deep learning technology we have called deep learning superscaling to up resolution it. And it looks like you rendered at the higher resolution, but the cost of that up resolution from a network trained on lots of images is far less than rendering it at the native resolution. The other, and this is really what enabled real-time ray tracing, is deep learning denoising. So we have been doing ray tracing in our professional graphics for ages, but it would render at like 1 or 2 frames per second. And even once we added the RT cores, it might have rendered at like 10 or 20 frames per second, but gamers want 60 or 120. And so what we do is we actually ray tracing is a Monte Carlo simulation of light transport. And if you do fewer rays per pixel, you get an image, but it's a noisy image, right? So rather than cast the 10,000 rays per pixel that Disney will cast when they're doing ray tracing for a feature film, we'll cast like 5. And what you get is it's the same kind of image you get if you take a photograph at a very high ISO. It's all there, but it's kind of grainy. And then we'll feed it to a deep network and it'll clean it up, make it look like you cast 10,000 rays. That's on the graphics side. And then the other side with Omniverse is we have built into Omniverse lots of physics simulators. And we're starting to convert a lot of our physics simulators to, rather than actually executing the partial differential equations, we learn the partial differential equations with the neural network and then do the simulation through inference. So I hope that answered the question.
Okay, thank you. Is it a better idea to create general deep learning accelerators for all applications, or creating specialized deep learning accelerators such as vision accelerators, natural language processing accelerators, etc.?
I'm a full believer in making things as general as possible without giving up efficiency. And we've been able to match the efficiency of dedicated accelerators with our GPUs. And what's really important is that this field is moving at an amazing pace. A couple of years ago, people were using RNNs for language. And then transformers came along and boom, RNNs went away and everybody's using transformers. And similarly, just a few years ago, everybody's using convolutional neural networks for images. And a lot of people still are, but I see the switch happening where people are now moving to image transformers for images. So I think it's very dangerous to try to over specialize and build an accelerator just for one form of network. Because with a design cycle time of a couple of years, by the time you're done, it may be very likely that that's not the network people are using anymore. And you need to be flexible enough you can track those changes. They're still happening at an amazing rate.
Okay, I'm not going to skip any questions. If you think it's simple, you can skip it. What is the impact of Moore's law on GPU performance and memory consumption?
Well, first of all, Moore's law is a law about the cost of transistor scaling over time. If you go back and read his paper from Electronics Magazine and was it 64 or 65, and it's largely over, right? We still get more density, but the transistors aren't getting cheaper. I can look at our jump from 16 nanometer to 7 nanometer, and yeah, we got a lot more transistors, but the cost per transistor didn't go down. My first answer to the question is that Moore's law, as it was stated by Moore, is kind of dead. Still, getting more transistors is a good thing. It lets us build bigger GPUs, but they're going to be more expensive GPUs and they're going to burn more power. But it's still good to have the additional transistors. It enables us to build things we couldn't build before.
Okay, when a GPU is made of multiple chiplets, is it practical to combine one graphics chiplet with multiple FP64 chiplets to make a GPU with both graphics and FP64 like V100? And then I'll ask you the second part next once you're done.
Well, our GPUs aren't built for multiple chiplets. We're still building, monolithic GPUs. And we have debates about this every generation, but when we do the analysis, it turns out the most efficient and cost-effective way of building our GPUs today is monolithic. And we will revisit this every generation, I'm sure. So, it's kind of a hypothetical question. You could do anything. We don't do that. We build a monolithic GPU. And in building a monolithic GPU, we then need to decide, when we, start, do the design for that chip, what function units we're going to put in that. And we do subset our SMs for different markets. So we'll build different GPU chips. Only the very high-end chips that we have FP60. They all support FP64. Only the very high-end ones have really good FP64 performance, because what we realized is nobody builds a supercomputer out of those low-end parts. So why burden them carrying the area overhead of the FP64? We've made a big commitment to have every one of our GPUs have tensor cores in them. It's kind of like the commitment we made back when we first launched GPU computing. We had this saying CUDA everywhere, and we pushed the support for CUDA into our very low-end parts. So even people who had a relatively low-end GPU on their laptop could write CUDA code. And I think it was a very successful strategy that really caused a lot of people to move to CUDA. In a similar way, we have the tensor cores very, very far down the line. So, and that's also so we can use them for graphics, right? So we can do the denoising and superscaling and anti-aliasing, using deep learning and graphics.
Okay, the next question: how would FPGA-based accelerators compare to GPU-based accelerators?
Yeah, that's a good question. So it's really a matter of whether you're using LUTs to build your deep learning, or whether you're using hardwired units in the FPGA to do your deep learning. If you're using LUTs, I think you're just going to lose, because we did a study of this a while back, and we found is the overhead in both area and energy of building something from a LUT rather than building it from gates, from a hardwired ASIC approach, was close to 100x. And so it's tough to make up with configurability 100x that you're losing due to the overhead of the LUT. Now that said, most FPGAs have a lot of pretty good hardwired logic on them. Things like arithmetic units, some of the FPGAs have their DSP units, and they've got nice RAM arrays, they've got gobs of on-chip SRAM bandwidth. And so you can configure those and not be down too far, but I still don't think you're going to do as well as something like a tensor core, which is a pretty nicely designed, matrix multiply accelerator.
Okay, how does distributed computing with NVLink work? Who decides which computation will run where, and what are the overheads of having to do a scatter-gather across multiple GPUs?
That's a really good question. So the programmer decides where to put both the data and the threads. You launch them on the GPU where they're going to run. You have the advantage in an NVLink connected system that it's a shared address space. So the overhead of doing even relatively small data transfers is pretty small. And we have collective operations, in our network. So, typically what you do in deep learning is if you're doing, a data parallel approach, you basically have each GPU running the same network, but with a different portion of the data set. And then they accumulate weight gradients and go through a phase where you basically share the weight gradients over all the GPUs and accumulate the overall gradient, add that into the weight. And the collective communications are very effective at doing that.
Okay. Who do you view as your biggest competitor?
Ourselves. So we're constantly trying to disrupt ourselves, and I think that's the right way. I think that if we looked at other people to be our competitors, it would slow us down too much. So we want to kind of set the stake. And the other way I like to look at that thing is, we're not so much worried about what everybody else is doing. We're worried about what is possible. We often compare what we do to the speed of light. What is the best we could do, and how close are we coming to that? And that's the competition.
Who in the academic space would you like to partner with, and why?
Oh, that's a good question. I think we're already partnering with most of the people we want to partner with. Rather than try to go through a huge list of who those people are, what we tend to do is we tend to try to find what we think are challenging problems that are holding us up from getting to where we want to be. And then we ask, who is doing the most interesting research in this area? And we go talk to them and find out how we can work together with them. We've also evolved to the point where we have a bunch of people at NVIDIA. I think I have something like 15 of them now who report to me, who are part-time academic, part-time NVIDIA. So for example, our robotics lab up in Seattle is run by Dieter Fox, who is 50% NVIDIA, 50% on the faculty at University of Washington. And that works really well because it gives us, it sort of plugs us very intimately into a lot of different academic institutions. That gives us the ability to keep an eye on research that's happening often before we would otherwise be aware of it.
Do you see quantum simulations as a natural extension to these deep learning challenges, and what are your thoughts on quantum computing?
So we just announced at not the current GTC that just happened in November, but back in March, a package we have called cuQuantum. And so we were able to take the Google, I forget what it was, 57 qubit or whatever thing that they did that they claimed was quantum advantage. There was a calculation that you couldn't do ever on a classical computer. We did it in 5 minutes. So we see that GPUs are probably, if what you want is to really do an accurate quantum algorithm and not the NISQ, the noisy intermediate scale quantum computations you can do today, GPUs are about the best way of doing that. So in one way, our classical GPU computers are the current fastest quantum computers. There's also a really nice result from Alibaba recently of a similar kind of classical computation. So our view on quantum, one of the things I'm charged by is to make sure NVIDIA doesn't get surprised by something that happens in the technology space. And so we actually have a study group where we track every result that comes out in quantum. IBM just announced there was a 127 qubit chip. And so we're tracking the progress in number of qubits and noise of qubits and coherence times. And it is not going to be commercially relevant for the next 5 years at least, and probably the next decade, because the number of bits you need and the accuracy of the bits, people are still, to the 1 to 2% noise level in these qubits, and you need to get the noise level to somewhere in the 10 to the minus third to 10 to the minus fourth to be able to start getting quantum error correction to work without huge overheads. And then you wind up needing order of thousands, in some cases, close to 1 million qubits once you put the overhead in to get on the order of a few thousand ideal qubits to be able to do reasonable computations. I think, my most optimistic views in maybe 5 years' time, people will start doing quantum chemistry simulations, which is probably the closest match for that. But I think it's a lot of tough physics for people to get through before they get to that point. What a lot of people don't realize is quantum computers are analog computers, and they have to be analog computers that are extremely precise and extremely well isolated. Any coupling to the environment is an observation that causes you to lose your coherence.
Okay, the next question, and we have about 2 more minutes.
Okay.
If developers are focusing on frameworks, in parentheses PyTorch, what should they learn from hardware advances to make their deep learning models run faster or more efficiently? Deep learning courses largely skip on GPU architecture.
Yeah, that's a really good question. And it's a hard one to answer because the frameworks do a great job of abstracting the hardware away. But there's still things you can do that will run fast or run slowly. I think one of the things we try to do is when we come up with a better technique, and often it's better number representation, FP16 or TF32 or using VS Quant, we try to take our version of some of the frameworks and put those techniques into it, so it's easy for people to exploit. But there's probably no substitute for trying things a couple different ways and seeing which one works better.
We do have about 7 more questions. Would you like to keep on very quickly answer them?
Yeah, I'm happy to go through them. It's only 7. Yeah.
Thank you very much.
Yeah.
You talked about memory bandwidth with HBM, etc. How is that computed? Is it across all GPU cores accessing memory simultaneously?
So it's not really about the GPU cores, right? We have a separate frame buffer partition for each HBM stack. So for example, in Ampere, there's 6 stacks. Our memory bandwidth is computed with each of those memory controllers operating at full bandwidth. There's a layer of cache between the GPU cores and then our on-chip network. And that network is many times the bandwidth of the HBM. So we can basically, running even a fraction of the SMs, saturate the HBM.
Okay, when do you expect machines to have human-level general intelligence?
Well, I'm a pessimist about that. I mean, if you look at what has been successful in AI, it's building neural networks that essentially are universal function approximators. They can learn a function by observing it. And they're most valuable for things that you can think of as artificial perception rather than artificial intelligence, right? They're things that recognize images or recognize spoken words or change words from one form to another. I think, you have to define a little bit what, AGI is, but I think we're a long way from there. And I think we've had huge successes and we'll continue to have huge successes in using, AI and deep learning to, increase productivity, make people's lives better, improve our healthcare, improve our education. And we don't need AGI to do that. We should, focus on what gets us the maximum advantage from what we do know how to do.
There is an old saying that pessimists are well-informed optimists. So the next question, which is the closest company that is approaching the advancement of your technology?
Oh, again, I like to compare ourselves against what's possible rather than against competitors. So, it's hard to say.
Okay, how does your Tensor Core compare with Google TPU?
That's a good question. So, I have to compare against the TPUs they've actually written papers about. So the latest TPUs we don't know so much about, but their historical TPUs have been much more specialized engines, where they basically have had a big, MAC array, whether it's with int8 for the original TPU1 or with bfloat for the later TPUs for training. Then they have a separate unit to do the sort of nonlinear functions and the batch norm and things like that. Whereas our approach has been to build a very general purpose computing unit, the SM, with a completely general instruction set. You can program it to do anything, and then accelerate the matrix multiply part of that with the Tensor Core. So they're similar in that they both have these MAC arrays. One difference even there is our MAC array is relatively small. I mean, the FP16 bfloat 16 MAC array is a 4x4 matrix multiply. It does just 16 multiplies per cycle, and then we have a lot of those to get our numbers up, where they have, I think, a couple really big ones. So I think they're much more specialized and coarser grained would probably be the way I describe that.
Is NVIDIA experimenting with the new packaging methods?
We are always experimenting with everything. So we have projects in NV Research doing multi-chip modules, doing chip stacking with solder lumps, doing chip stacking with hybrid bonding. There are a lot of neat technologies for packaging, and I think because moving data around is so important, a lot of those packaging technologies will be important in the future. And I view our job in research is to experiment with these technologies, understand what they can do, what they can't do, and queue them up so they're in the repertoire of things that we can then use to deploy in a product when the time is right.
Okay, and the last question, there are a few very specific other ones that I'll skip. The last one is, which NVIDIA's SDK do you feel are the most advanced in terms of leveraging the newest emergent features you've discussed?
That's a hard question to answer. I'd like to think all of our SDKs leverage our new features, because we build our software stacks in kind of layers, where at one layer we have CUDA, which is the basis for everything, and then on top of CUDA we'll build cuDNN, and on top of that support for the different frameworks, TensorFlow and PyTorch and stuff, and then on top of that we'll build the stacks for robots with our Isaac software, and our stacks for autonomous vehicles with Drive AV, and our stacks for smart cities with Metropolis, and so on. I think all of these SDKs are great. It's more that different SDKs are targeted different applications, different verticals, and not so much that one is better than the other.
Okay, well, thank you very much, Bill. If you don't mind sending me the slides,
I'd be happy to do that.
On our website, a number of people asking for slides for your patent, and then as soon as possible, I will also produce the video. Thanks again.
Thank you, and everybody have a happy Thanksgiving.
Thanks. Happy Thanksgiving to everyone. Bye.